So hello again. For this lecture, I'm happy to introduce our next invited speaker, Maurizio Filippone, who is Associate Professor at EURECOM, France.
Thanks, Nadia. It's a huge pleasure to be part of this fantastic event. I would like to take this opportunity to thank the organizers for making me part of it and for the impeccable organization. So today I'll be talking about something that you may have heard, not heard so much, deep Gaussian processes. So this morning you've had a lecture on Gaussian processes and the application on Bayesian optimization. What I'll try to do today is to give you a bit of an overview of what these deep Gaussian processes are and try to sparkle your interest in these models and well, try to draw some connections with current state of the art on Bayesian inference for Bayesian deep nets. So I divided the talk in a few sections. I'll start with an introduction to what Gaussian processes are, very briefly, so just as a refresher for this morning. And then I'll dive into what deep Gaussian processes are. And then I'll show you, well, few ways in which people have, come up with to carry out inference for deep Gaussian processes, which is actually pretty hard, as I will try to motivate and convince you of. And then, well, when we talk about deep learning, of course, we cannot avoid the fact that certain kinds of representations really give you a big boost in performance. So if you just use a Bayesian deep net without convolutional layers to learn C410 or MNIST, you're going to reach certain performance. But of course, as soon as you introduce convolutional layers, then performance go up a lot more. So is it possible to combine convolutional deep neural networks with deep Gaussian processes? So this is the kind of work some people have been working on in the last few years, and also our group has been actively involved in this. And then I'll draw some conclusions. So most of the technical details will be skipped in this presentation. I thought that after 5 days of this kind of summer school, it would be full of equations in your head. So I tried to make my presentation very visual, a lot of diagrams and figures, and I hope you'll appreciate that. All the details there will be a long list of references at the end. You can catch up a lot of these details on those. Right. So first of all, let's talk about what Gaussian processes are. You've seen this morning. So the way I think of it is a prior of a function. So when you draw from a Gaussian process, prior, you draw functions, okay? So this is the illustration I have. So imagine you have a real line, and the real line indexes an infinite number of Gaussian random variables, and jointly, therefore, these random variables are Gaussian, because if marginally each of these is Gaussian, jointly they will be Gaussian. And what we impose here is some sort of covariance across these random variables, which can, for example, depend, in this example here, can depend on how two random variables, how far they are. Okay, so you can imagine that for each point in the real line, you have associated one particular random variable, which is Gaussian. And if you impose this spatial structure, immediately you're gonna get the random variables that nearby will have to covary a lot. Okay, and if they have to covary a lot, then you're gonna get some sort of patterns of how these functions behave. Okay, so here what I'm showing is a bunch of different draws from these Gaussian processes when we change what we call covariance parameters, here denoted with this squiggly symbol here. So if you remember, covariance functions are parameterized through a so-called covariance function, and the covariance function as a parameter itself. Okay, so depending on how you tune these parameters, you can start achieving different kinds of patterns of variability for these functions. So in this left example here, we have functions that are quite smooth. And then here, for example, we can have functions that are much rougher. And here we can play around with another parameter to establish some sort of different marginal variance for these variables. Okay? Of course, this is our prior now. Okay? So we can think that we can construct these kind of priors for functions. But how do we actually, well, first of all, make it tractable? So here we're talking about an infinite number of random variables. So how can we make it tractable, first of all? And second of all, this is just a prior. Then how do we use this prior to do inference? Okay, so then we want to learn functions given data if we are Bayesians. Okay. Okay, so first of all, I would like to talk a little bit about this connection between Gaussian processes and infinitely wide shallow neural nets, which was talked about in Radford Neal's thesis in 1996. So imagine to take a shallow neural network. So you have in this case, you have a three-dimensional input, and then we're going to have an infinite number of neurons in the middle layer, and then the output layer here. Okay? So denote X by the input nodes, phi the nodes in the middle layer, and F the layer at the the output layer. Okay. So imagine now that you have Gaussian priors on W0 and W1. Okay. Well, the central limit theorem tells you that the output F will be well, if the Gaussians have zero mean, then the output is going to be zero mean. Okay, so F is going to be Gaussian with zero mean, and the expectation, well, the covariance is going to be this expectation here, where what we do here, we pass now by X here, I denote the matrix which is going to be infinite by 3. Okay, and then we multiply by W0. Okay, and we apply some nonlinear transformation, and then we apply by W1. Okay, so given that F is this guy here, well, here what I'm writing here is the expectation of FF transpose. Okay. And then I have to compute this expectation with respect to W0 and W1. So if you do that, the expectation with respect to W1 is pretty simple. Okay, so this is just going to be the covariance of W1, okay, which is alpha 1. Okay, so alpha 1 can go out. And then you are left with this expectation here, which is simply an integral. Well, simply, it's actually an integral with respect to this distribution over W0 of this thing, which is a nonlinear transformation of the input and the weights. Okay, so this expectation is going to be an integral that, in general, we may not know how to treat, but actually it turns out that for some choices of phi, of the nonlinearity that we apply there, we can retrieve various famous kernels. So the RBF, I believe, is what you may have used in the lab today to do your Bayesian optimization. But of course, there are many others, Matern, Arcosine, and so on. Okay, so this was pointed out already many years ago. So this is one way to think about Gaussian processes. Another way to think about Gaussian processes, as I said before, is that we have this infinite number of random variables indexed by the real line. So if you think about it, when you look at these random variables here, denoted in light blue, I hope you can see it, then all these random variables lead to a covariance matrix which is infinite by infinite. Okay, so it seems quite awkward to work with something like this. But actually, it turns out that we don't really need to do that. Imagine that we have only observations here where you see the orange points. Okay? So then what happens is that the theory of multivariate Gaussians tells us that if you have a multivariate Gaussian and you're only interested in a bunch of these Gaussian random variables, what you can do is to take the covariance of these few random variables is going to be obtained by taking the full covariance and just selecting the rows and columns corresponding to the points where you have data. Okay, so which means that if I have a bunch of points here, what I can do is to just select the rows and columns corresponding to the points where I have data. Okay, so I end up therefore with something which is n by n. Okay, so in theory everything is infinite, but in practice we don't care because the Gaussianity allows us to work with something which is only n by n. Of course, this is great, because now this is returns to the domain of finite things that we can kind of deal with. But now, of course, this is multivariate Gaussian. This is a covariance matrix, n by n. And if you remember the formula for multivariate Gaussian, then you have a log determinant for k, and you have a quadratic form that involves the inverse of k. So that requires somehow to be able to do algebraic operations with k. And if k is n by n, if you remember your linear algebra courses at the university, then you should know that inverting, calculating log determinants is done in a nice way if you go through the Cholesky decomposition of this matrix. And the Cholesky decomposition of an n by n matrix will cost you n cube operations. Okay? So this is, you may have realized today when you've done your exercise that actually this is quite costly, okay? And already if you start thinking about a few thousand of observations, it becomes very, very slow on computers. Also, the Cholesky algorithm is kind of serial, so you cannot really easily parallelize it. Well, you can, but you don't gain so much. Okay, there's a lot of serial computations that you have to carry out in order to be able to do the Cholesky. And if you have a lot of RAM, you can actually, yes, factorize big matrices. But with current hardware, we could push this to between 50,000 and maybe 100,000 if we are lucky, with a distributed implementation where we have parts of the matrix sitting on different machines, and then there is a whole coordination to do this big Cholesky. Okay, so here I'm talking about 100,000 if we are lucky. So on your laptop, probably you can do 10,000. Okay. So then immediately you start thinking, why should I use Gaussian processes? I mean, I do deep learning. You give me 15 million images, I can do it. Minibatch, and I'm good to go, right? So can we use Minibatch here? And we'll talk about it in a minute. But first of all, I'll give you a couple of illustrations of how to use Gaussian processes, and this is pretty simple, and I believe you've implemented part of this in this morning. So just for convenience of notation, whatever we observe, I color with orange, okay? And the latent variables blue, okay? And parameters of the Gaussian process will be this sort of orange-yellow, and the weights of neural networks is going to be green, as you've seen before, okay? So that there is colors for each symbol, and it should help you with the notation. So we have inputs, X, and we have labels Y. So X is a matrix n by d, okay? N number of observations, d number of dimensions. And Y is the labels, number of observations times number of outputs, okay? So what we can do is to introduce latent variables, f, with covariance k, okay? And k, as we said before, is going to be a function of your inputs and the parameters of covariance, okay? And then we introduce a Gaussian likelihood. So we say that P of y given f, if we are in a regression example, P of y given f is going to be distributed as Gaussian. Okay, so this is very similar to what people do in linear models, generalized linear models. So what you have is some sort of linear combination of the features, okay, that gives you a linear function, and then on top of that you add your likelihood. Okay, here is no different now. The only thing that changes is the fact that we look at a prior over my functions directly instead of a prior in a Bayesian linear model, instead of a prior on the weights that you used for the combination of the features. Okay, so there's a nice connection there with the generalized linear models. Okay, so the posterior now of your functions given y, x, and theta can be just computed like this. So now we have our Gaussian process prior here and our likelihood. And of course, if we are in the Gaussian world, so we have a Gaussian likelihood and Gaussian process prior, the posterior is going to be Gaussian. Okay, so the posterior over the function values at each of these locations where I have data is going to be multivariate Gaussian. Okay, across the points. So I mean, the way to solve this is pretty simple, because when you have the likelihood and the prior, you multiply them together. You don't really need to think too much about the normalization, which is usually the hard bit in Bayesian inference, because you know automatically how to, as we say, complete the square. Okay, so we just look for the mean and the covariance of the product of these two guys. Okay, and we realize that there is a quadratic form for f with a particular covariance and a particular mean. Okay, and now if we do that, now once we have that posterior, now we can also extend to f star, which means we look for what happens outside of the domain. Okay, so we look at places where I don't have data. Okay, and what I do is I weight my conditional distribution of P of f star given f, which is going to be Gaussian, okay, because all these Gaussian variables, f and f star, so where I don't have data, are going to be jointly Gaussian, because this is a Gaussian process, okay? And then I can weight this by the posterior distribution over f given data, okay? And what I get here is get P of f star given data and my covariance parameters. So I integrated out here the latent variables f. And if you do that, that's the kind of picture you get. And this is one of the reasons why I kind of fell in love with Gaussian processes, because I thought this would be a very elegant way of thinking about how to do inference for problems where you deal with functions. Okay, so I don't give you the mathematical details. You can find everything in Rasmussen and Williams' book. There is a beautiful derivations, very simple to rederive and implement. Okay, now let's think about classification, for example, where things start to kind of break down already. So we have, again, inputs and labels. Now labels are going to be, you can think of it one-hot encoded, for example, if we do multi-class. But we can imagine here a binary problem where we have, we're trying to classify squares versus triangles, okay? And imagine that this is the function I use to generate my data. So this is the probability of class triangle, okay, over the input domain. Okay, you see here there is a higher probability to draw a triangle, and here as well, and then here there is a lower probability, so there is a higher probability to draw squares. Okay, so again, I can proceed similarly to as the same way we did before. So we have a likelihood, which is now going to be some sort of Bernoulli likelihood. Okay, and the probability now for these class labels, it has to be squashed between 0 and 1, okay? So again, in generalized linear models, what you do is to take your linear combination of the features, you apply some transformation to squash everything between 0 and 1. Here's no different. We do the same thing. So we take f, our latent functions, that are unbounded because these are Gaussian processes. So marginally, they are Gaussian, so they have unbounded domain. And we squash it between 0 and 1 to become a probability. And then on top of that, we add this Bernoulli likelihood, which establishes the probability of class labels. Okay? So now we have a Bernoulli likelihood here with a nonlinear transformation of f, and then we have a Gaussian process prior. If you are, so things break down here because now there's no way you can make this integral, you can calculate this integral analytically. So there's no way you can get a closed form solution for your posterior. Okay? But let's say that we can do some approximation. And imagine what we're going to do. Well, we do Gaussian approximations, just because Gaussians are nice. And so if we do this Gaussian approximation, actually we end up with something which looks like this, which is pretty okay. So in this particular case, I think I used a famous algorithm to do this approximation of this posterior distribution, which is called expectation propagation, which I'll tell you a little bit about maybe further on in the talk. And this is the kind of functions you get, okay? And again, these are all bounded between 0 and 1 because we have this squashing that squashes everything between 0 and 1. And it looks pretty nice, yeah? So we have ways to treat also classification. And of course, now you can think of any likelihood you want. You want Poisson likelihood because you're modeling counts. Well, we can do it, okay? So there are ways we can actually approximate this posterior in some ways, okay? Okay. But you see that already classification, that is kind of one of the most famous tasks in machine learning, is already pretty hard, okay? Because already here, nothing is analytic. So if you want to be Bayesian here, you have to do some work, okay? And the same thing happens in the case of generalized linear models. So for generalized linear models, if you want to be Bayesian, you have to do some sort of approximations, yeah? So this is the same thing. Okay, so this was already a hint to the fact that when sometimes you cannot compute this marginal likelihood, okay? So the marginal likelihood, if you do this integral here, you get P of y given x and theta, which is called the marginal likelihood, okay? This P of y given theta might not be computable if your likelihood is not Gaussian, okay? So this is a graphical model now. So for those of you that are mostly familiar with diagrams for neural nets, this is not, okay? This is a graphical model. So here I'm shading the variables that we observe, x and y. And graphical models are used to denote the conditional dependencies between the variables. So we have P of f, which is conditioned on x and theta. And then we have P of y given f, okay? And as we said, if P of f given x and theta is a Gaussian, and P of y given f is Gaussian, then everything is good. However, we have to invert this big matrix. We have to factorize this K matrix, okay? So as soon as you give me more than a few tens of thousands of points, I'm saying, okay, I can't do it. Or it cannot be computable even, because as I said before, if the likelihood is not conjugate to the prior, we know that we need to do approximations, okay? Okay. So that's pretty bad, no? Why do we do Gaussian processes? And also there is another issue here, which is kernel design. So I showed you some samples from the prior before, and they look kind of smooth, okay? Then you can make it rougher, but then people can come up and say, oh, you know what, there is a linear trend here, or maybe there is some periodicity. So you start entering this world of kernel design, okay? So how to find a good kernel for your problem. Of course, if you're Bayesian, you can say, well, I can use the marginal likelihood as a proxy for doing model selection. So I can have a bunch of kernels, and I can compare using Bayesian techniques, for example, Bayes factors. But yeah, this marginal likelihood is not available analytically. So you can start thinking about, maybe I can do some sort of compute this integral with Markov chain Monte Carlo, which may be a bit more accurate. This is what I've worked on a lot in the past. But it's pretty hairy, again, because remember here that everything depends on this K matrix, which is going to be n by n. And when n is large, you can have your Markov chain Monte Carlo algorithm running for a month. And, for maybe dealing with a problem of 5,000 observations, okay? So the issue of scalability is really important, okay? This is one of the topics of this school, of course. But for Gaussian processes, this has been, a problem that people have been working on for a long time now. I hope I convinced you that even just simple Gaussian processes lead already to interactabilities that make your life quite hard. So now I wanted to focus a little bit on kernel design as well, because I think it's a very interesting topic and leads to the definition of deep Gaussian processes, or at least the intuition behind why it's useful to do deep Gaussian processes. So imagine now I have two functions, two processes, okay? So I deliberately made them a bit nicer and smooth so that you can see what's going on here. So you have, imagine you have F here and G here, and these are two processes. So what happens if I compose the realizations of these processes? You see that these processes are kind of smooth, okay? And as soon as I compose, what I get is something which is kind of strange. It starts to behave a bit more erratically, and also the uncertainty around starts to have weird patterns. So you see here there is larger uncertainty than places like here, for example. And so immediately you start thinking, well, if I start now composing these sort of simple functions, then we're going to get something complicated very soon. And this we know, right? So when we do deep networks, that's effectively what we're doing. We're composing functions. And in that case, they are parametric. In this case, are Gaussian processes. Okay? But the philosophy is very much the same. So composition helps you to say, take something simple, compose it with something simple. You can get something which is pretty crazy, okay? Which is good. You immediately expand the capacity of your model just by composing. So now the graphical model I show here is what we had before. So we have a Gaussian process prior over the first function, f. And now we just say that this function f becomes the input to the second layer. So to a second Gaussian process that is going to take f1 as the input. Okay, and this Gaussian process is going to have its own kernel parameters, and then we have observations. Okay, and then we're going to have a likelihood on p of y given f2. Okay. And so now we've constructed this hierarchy here, and this is what we refer to the deep Gaussian process. Okay, any questions so far? Everything okay? Pretty simple? Yeah? Don't hesitate to stop me if something is not clear, okay? All right. Okay, and so you say, okay, now I can go crazy with this. I can go as deep as I want, right? So I have this machinery now that draws samples from the prior, and it's easy to draw from the prior, right? So you can draw the first function, and then that feeds into the second the construction of the second covariance. Then you draw the second layer, and then you keep going, right? So you can go crazy as much as you like. And what happens here, I hope you're seeing but the color is pretty light, unfortunately. I don't think you can see very well. I'll try to explain with words then. On my screen, it looks beautiful, but unfortunately. So if you have one layer only, you get these nice functions. Well, if you download the slides from my page, you can actually see it pretty well, I think. So you have smooth functions here. And then as you start composing, things start to become a bit more interesting, I would say, in the sense that you start getting jumps between, the function is able to jump a bit more, okay? So you're composing things that are kind of smooth, you start getting things that start to jump a bit more. But then, soon enough, when you increase the number of layers, when you get to 10 layers, I don't know if you can see, but these are pretty much flat lines with some sort of dent on top, right? So it's like a weird degenerate prior now. So my functions now, if I start composing a lot, become something which is not very useful. Okay, I would never use a prior like this to model any data because this is just a flat prior, a flat function. Okay. And in order to construct this prior, we did something super crazy, super complicated, because we stacked 10 Gaussian processes one on top of another. Okay, and the kind of prior we get is completely useless. Okay. So not necessarily going deep is good, and I think, okay, we know this lesson also from other works on deep networks. And what was proposed already back then in 1996 by Ralph O'Neill, and then studied in this beautiful paper by Duvenod and others in AStats 14, where there are beautiful illustrations about the pathologies you can get with these deep Gaussian processes. The illustrations are simply amazing, okay? So I recommend to read this paper if you're interested. And what you start getting now, so the only modification is to shortcut the input X to each layer, okay? So by doing that, then what happens is that you feed the input in a way that you also sort of make it a function always of X, okay? And this is a similar idea that people have proposed in, I think it's called the residual network paper that came out a couple of years ago. So where you try to shortcut layers, okay? So you put the output of a layer, a few layers down the architecture. Why is that? Well, learning the identity function is pretty hard, okay? Even with a deep neural network, if you want to learn the identity, it's pretty hard because your weights have to align in a way that is not very convenient, right? So if you explicitly say, well, there is an identity plus something, that's a much better way to work, right? So effectively, what you learn here is some sort of differential representation from the identity, okay? If that makes sense to you, okay? So and you can feed this to any layers down the architecture, okay? There's also a paper by Alex Matthews that came out just, I think, a month ago on this. So we talked about this pathology of going deeper, but we can kind of solve it, and that's great. And now, okay, now let's do inference with this. Now I have a model that I'm okay with it. The prior functions I get are quite nice. If you can see what's going on here, these functions are actually much more complicated than this, so I increase the capacity, but still they look useful for inference, okay? And now I want to do inference with this. So I'm given data, and now I want to compute, for example, the marginal likelihood of my model. So I want to compute P of y given x given theta, where theta now is the theta across, all the thetas of all the kernels at all layers. Well, if I want to do this, now I have to do P of y given f at the last layer, and then P of f of the last layer given the one at the layer before, and so on and so forth, times. And then I have to integrate out all latent variables at all layers, okay? Well, if it was hard to do GPs, imagine now doing deep GPs, right? So now we have many more integrals to solve, and things become very hairy very soon. Okay, so how do we do it? Well, we've witnessed the deep learning revolution in the last few years. And a lot of the ingredients, I think, really played a big role in this, I think, are the following. So first of all, we talked about large representational power. So if you start going deeper with these models, you can really go, construct crazy-looking functions that can really model very complicated things. And one of the keys, I think, is also the fact that you can exploit mini-batch-based learning. So you can just chunk up your data, just throw it to a lot of machines that can compute in parallel. You can do stochastic gradient asynchronous, synchronous stochastic gradient descent. You can do a lot of things that really help you to parallelize computations. And at the same time, also the fact that you can exploit GPU, well, I should say also TPU now, tensor processing units, because a lot of these computations can just be done using tensor products. So in deep nets, this is all great. And also, I think one of the really the biggest advantages that we've seen in the way we can implement now models is automatic differentiation. So I'm a bit older than you guys, and when I started, I remember I was calculating derivatives of my objectives, and then implement them and debug them, spend days debugging and so on. And now, if you have a very deep network, which is very complicated, you want to do maybe some sort of variational inference, so you have parameters that enter through reparameterization tricks and whatever. And writing the derivative yourself would take you a bit of time, and implementing it right would take you a lot of time. And now all this has been lifted because automatic differentiation has become something which is commodity. We can use it through TensorFlow, PyTorch, you name it, okay? And I think this is really a big thing that we've seen in the last few years. And of course now, large representational power is nothing if you don't have regularization. So the development of techniques like dropout, for example, for regularization really made sure that these networks could actually generalize quite well and achieve impressive performance in a lot of tasks. And of course, we talked about it, convolutional networks. When we talk about deep learning, many times we refer to the fact that we think about images and not only, of course, but just to say that application-specific representations can help. Of course, for text as well, we can think the same. Okay, and I just wanted to play a little video here about something you've seen in day 2, I think, on stochastic gradient optimization. So how does it work? So this paper dates back to 1951. So imagine that this is your objective, okay? And you are here with your optimizer, and then the gradient one step of the gradient will take you there, okay? So the way stochastic gradient optimization works is that now you don't have a routine that gives you the exact gradient, but it gives you, whenever you interrogate this routine, you get a different value, okay? And these different values have the property that the expectation of these gradients is the exact gradient. So the average of the positions where you land with this interrogation of this routine will take you, on average, to the right spot. Okay, so then if you have that, then there is this beautiful theorem that tells you that you're going to hit a local optimum, okay, of your objective, which is great. So now we can apply it as long as, sorry, I forgot to say that alpha goes to 0 with certain rates. Then, we know that there have been a lot of variations on the theme on how to do it, with momentum and so on and so forth. And here I wanted to play a little video on, which is PDF, by the way, which I think it's, it's just very impressive, okay? Making a video in PDF. So what I do here is to show you, this is a simple Bayesian linear regression problem, okay? And what you have here is that you have your points, and then stochastic variational inference, what it does is to learn a whole distribution over, to approximate your posterior distribution. So your posterior distribution is the black posterior over here, the black distribution over here, and the prior, when the movie finishes, it restarts again. The prior is somewhere, sits over here, okay? And as the procedure goes along, then I make stochastic steps, so using mini batches, for example, okay? And then what I end up with is something that is going to converge. My Q, as people call all approximating distributions, will converge to our true posterior, okay? And because this is a Bayesian linear model, so here I'm not using Gaussian processes, I'm not using fancy likelihoods, this is all Gaussian, Gaussian, Gaussian. Then I have 2 parameters, which are the slope and the intercept of this straight line, okay, that models the data. And everything should match, right? Because the posterior is analytic, is Gaussian. So if I use a Gaussian approximating distribution, my stochastic gradient optimizer should converge there. And fortunately, in my example, everything works, which means that this is a good way of, well, an alternative way, of course, to solve something which is very simple here. And what I'm learning here, just to be clear, so this is just an illustration on top to show how stochastic gradient optimization works. But here I'm learning effectively 5 parameters. I have 2 for the mean of the red Q distribution that moves to go to the posterior. And then I have the covariance I want to learn as well. Okay, the covariance is going to be 2 by 2, and actually I reparameterize so that I learn the lower triangular, representation of the square root of that matrix. Okay, so I parameterize this covariance matrix to be L transpose, and I try to learn L. So it's 3 parameters. So it's 3 parameters for the covariance and 2 for the mean. Okay, so this is 5 parameters that I try to learn here. Okay, this is a good check to see that you've understood. I've done it for myself to understand, to make sure that I understood correctly stochastic gradient optimization, mini batch, and now this code can work with a lot of things because now I implemented this in PyTorch. Now, if I can change the likelihood, it's very easy, and everything will work with automatic differentiation. And now I can change the model underlying. I can do now a Bayesian deep net, for example, and everything works as well. Okay? So this is the beauty of the portability of this way of doing optimization, well, Bayesian inference. Okay? Approximate Bayesian inference. So now, is there any hope for GPs and DGPs? So can we use any or all of these techniques that we've seen being so successful for deep neural networks? Can we use any of these for deep GPs or even shallow GPs? Well, first of all, I mean, one of the annoying things I've noticed is that Minibatch cannot be really done for GPs. So in a lot of the problems we see in recent machine learning is that the objective factorizes. Okay, so if you have this, then great. Okay, you can just do mini batches. You do your trick here to do the unbiased estimator of the objective, which then turns into, when you take the derivative, turns into an unbiased estimate for the gradient, and that's it. You're good to go. You can use the power of mini batching. But for GPs, this is not so easy. Why is that? Well, if you just look at the prior, well, the prior is going to be proportional to this thing here, x of this quadratic form on f. And the quadratic form is pretty bad because the coefficients of the quadratic form involve k inverse. So unless you solve k inverse, you don't have these coefficients. And if these coefficients, you had these coefficients, you could have done some sort of mini batching. Okay, so if k didn't appear as -1, but just as k, you could say, well, you know, this is a quadratic form. It's still a sum. I can still mini batch somehow. I can do some crazy tiling maybe of my quadratic form, you know, of my matrix to select things. And actually, this is what we can do in spectral clustering. So we have a paper on this, but completely off topic. But in this case here, for GPs, you cannot do it. I mean, if you do any naive mini batching, you're going to destroy the correlations between all the latent variables. Okay? So you cannot do it. I mean, you can do it, but you're going to get something which is no longer a GP. Okay? And people have done it, of course, you know, and they get also reasonable results when you want to scale to large data. But this is not really the way I think we should be doing inference for you know, large-scale GPs. Okay, so now the question that not only I asked myself, but a lot of people in the community asked themselves is, can we actually exploit what made deep learning successful for practical and scalable learning of GPs or DGPs? Okay, and well, the answer is that, well, actually yes. So we finally, after a few years of hard work, we managed to kind of achieve this. So this is kind of a take-home message that today, if you want to do a GP or a DGP at scale, we can actually do it. Okay, so we've done it for you know, millions of observations, tens of millions of observations, and we're going to see some examples as we go along. So when you hear Gaussian processes, don't be scared. Okay, we can do it. Okay. Right, inference for deep Gaussian processes. So here I'm going to give you, this is a list of papers I think are relevant for the kind of things I'm going to tell you about, inference for DGPs. And the idea really is to extend what people have done for shallow GPs. Okay, so in shallow GPs, people have come up with ways of approximating Gaussian processes to be able to scale and also to deal with the fact that the likelihood may not be conjugate. And there is a very influential work on Gaussian processes, on sparse Gaussian processes by Titius in AI Stats 2009. And so what people have done have tried to extend this idea to deep Gaussian processes. So the way they did it was to apply variational inference to the approximation proposed in this paper here, done at all layers. Okay, so there are the original paper by Damiano and Lawrence is the one that really takes this idea, and then it's been developed after by James Hensman and Neil Lawrence in 2014 to actually do mini batching. Okay, so they managed to find a way to express the objective in a way that was a sum over data points. And later, this was extended, well, very recently, to also account for distributions that are able to capture correlations across layers. I'll tell you about in a minute. Okay. Another popular approximation to Gaussian processes, shallow Gaussian processes, is FITS, which stands for fully independent training conditional. And what the group at Cambridge, led by Richard Turner, did was to come up with a way to do expectation propagation, which is a famous technique for to do approximate Gaussian processes, and combine it with this fits approximation at all layers, and then to do inference. Also, in this case, they could achieve an objective that factorizes across data points, so they could use Minibatch. And then very recently, I think this is maybe a few weeks ago only, I can't remember exactly if it's June or July, but there was a question on Monday or Tuesday about this, I think it was Monday, about stochastic Hamiltonian Monte Carlo for Bayesian deep nets. And there's this paper that came out just recently on deep Gaussian processes, where what they do is effectively do the same Titius 2009 approximation with sparse GP, and then apply Markov chain Monte Carlo through the stochastic Hamiltonian Monte Carlo, which is something you also see today, I think, later on in the lecture on Markov chain Monte Carlo. Okay, and then there is a completely, so this is I think, I mean, this is a matter of tradition, really. I mean, people have really liked to work with the inducing points approximation. So with inducing points, what I mean is that, you have n data points, you use m, so much less than n, to express the whole process over n data points, okay? So this is like an intuitive idea, right? So you use less variables to explain something which is much bigger. Another way that we came up, so this is, Yaringal and Garamani have it in ICML 16 in an appendix, and we independently kind of worked on the same idea, and then we published it in ICML the year after. And actually, the idea is, if you remember this idea of having, a Gaussian process is a shallow, infinite-wide neural network. Well, if you manage to truncate somehow this infinite representation, that becomes a Bayesian deep net, right? And then people have come up in the literature of kernels and Gaussian processes with way of doing this truncation, if you like, in this infinite dimensional space using random features. And I'm going to tell you a little bit about that later. And effectively, then this becomes a Bayesian deep net. And then with Bayesian deep nets, we can use all the tools that people have developed in the literature of Bayesian deep nets. But then the question is, well, I mean, you start with the deep GP, and then now you turn it into a deep net, and then you do variational inference. So why DGPs? Okay, so these are all considerations I'll try to talk about as we go along and in the conclusions. Okay, it's clear to me that there is something that's going on here, which is Oshibka na etoi sta. Okay. Ah, my image. Huh. This was the beautiful picture I had. My goodness. Without this, you cannot understand anything. I'm sorry. I'm kidding. There is, okay, I'll sketch it on the board, if I can remember Woodbury identity. Okay, so the way low-rank approximations work, so all these inferences for DGPs are based on this simple idea that you use less points to express something which is bigger. Now, the issue now becomes the following. So why do we get a gain in doing this? Well, the gain, we get it because, you remember we have to do this inversion of a big matrix, and the log determinant of this K matrix. Now, there is an identity, which is called Woodbury identity, that tells you that if you have a low-rank approximation to your matrix, what you end up with is something which you can compute in much lower time. Okay, so if you have an n by n matrix, and if you have a low-rank approximation that I should probably write here, so I'll try to write big so that you can see it. So you have n by n, okay? If you can write this as n by m, m by n, okay? Well, inverting this matrix K inverse, and imagine that this is called Fifi transpose, okay? And imagine also you have some sort of plus identity or something, okay? Plus lambda identity or something. So you have a diagonal here. Actually, the K inverse doesn't require n cube operations anymore, but you can compute in m cube operations. Actually, it turns out that there is another cost that you have to sort of add to this, which is m squared. And because n is greater than m, then this becomes effectively m squared. Okay? Okay, there was a beautiful picture that showed this. I guess if you download the PDF, you can actually see it, but it doesn't show on the slides, but that's fine. And so the idea is really simple. Is to say, okay, let's do it at each layer. Okay, so we can do this low-rank approximation, and let's do it at each layer. And this is what people that do inducing points would say, okay, for each layer, I have a set of latent variables f. Now I introduce new variables, which I call u, okay, which are again distributed as Gaussian. Okay, so it's another Gaussian, mini Gaussian process, if you like, on u. And now what we do, we introduce also pseudo inputs. So we say this u can be placed anywhere in the space. Okay, and now I can think of these positions z as parameters that I can optimize. So I can optimize. I can place my points optimally to explain my whole Gaussian process at each layer. Okay? And these are parameters that we can optimize jointly with the parameters of the covariance of the GP. And now we do the same at each layer. So it looks kind of cumbersome as a construction, but then variational inference targets Q distribution over the latent variables U. So you're going to learn a Q. So you can turn the crank of variational inference, so you write a lower bound. I'm not going to give you all these details, of course. You can read all this in this paper. Okay, and then in this paper here, Bui and others, HTML16, and then you learn a variational distribution over U, all the U's. Okay, it turns out that they don't really do expectation propagation the way. So this variational inference is actually expectation propagation here. Okay, so it's not really VI, it's EP actually. And EP usually the way it works is that you assume that your well, in this case you assume that your posterior is going to be, your Q is going to be Gaussian multivariate, and what you do is to leave one factor at a time. So you leave one data point at a time, and you try to predict. Well, you try to do moment matching of your Q with the actual Q of everything except that times the likelihood. Okay, so you construct this so-called cavity distribution. You take your Q, you remove one factor, and then you try to match the Q with the exact likelihood for that factor there. Okay. If you do that, it turns out that you can actually do DGPs. So what they come up with is they found this idea in another paper before. I can't remember the exact reference now. And what you can do here is to just rewrite your Q as the prior over U times a G that you actually learn. Okay, and this G here is shared across all the data points. Okay, it's a bit technical, but if you derive the whole objective of expectation propagation, you end up with something which reduces memory and allows for factorization of the objective. As long as you project the Gaussian at each layer, so whatever you get from each layer, you reproject it onto a Gaussian distribution. Okay, so it's very intricate to explain it in one slide, but the gist is that you have a low-rank approximation for each of the covariances of the points here of the Gaussian processes, and then you learn through expectation propagation with this variation of expectation propagation that uses this average data factor. Okay. Okay. Instead, in the framework of Titius 2009, what was proposed is quite clever, actually, is the same construction as before. So you introduce these latent variables, you have pseudo inputs that you can optimize and so on. But then the target, when they apply variational inference, is actually a posterior distribution, an approximate distribution over F and U jointly, okay? And because they're all Gaussian, everything is, can be expressed, you can express easily the conditional of F given U and the U given F, of course, and everything. Everything is Gaussian. Everything is a Gaussian process, okay? But now the clever bit here is that in this approximation here, you actually augment the space somehow. So now you're trying to learn a distribution of a bigger space. But what happens is that really, what they do is what Titius proposed was to rewrite this Q approximation as the actual conditional of F given U, and then Q of U. And then they try to learn Q of U, okay? Again, if you do this for deep Gaussian processes, as shown in Hensman and Lawrence 14, actually the lower bound factorizes across training points, so you can do mini-batch, perfect. And recently in Salimbeni and Deisenroth 17, they showed how the marginal, well, the objective, sorry, let me rephrase it. So if you look at the distribution at the last layer of a single variable, that depends on the ith, so on the same index, ith marginal across the layers. So with that realization, what they can do is now to propose approximating distribution that completely factorize within layers, but that covary across layers. Okay, and so that gave them some quite good performance that we haven't managed to test and compare with our method. But in their paper, they achieved state-of-the-art performance compared to previous work working on inducing points. Okay, so now another way of doing this sort of factorization of your covariance matrix is as follows. As I said before, you know, we have a Gaussian process, a shallow net with an infinite number of neurons. But now if we look at the ways in which we can express, for example, a covariance matrix. Imagine that you have a covariance which is shift invariant, which is the case for the RBF, squared exponential, as you call it, maybe, and Matern, for example, and arccosine. Well, you have many here you can use that have this property. Actually, you can show that this is the Fourier transform of a measure P of W given theta, and actually, you can imagine that if this guy is Gaussian, then the Fourier transform is going to be Gaussian again, yeah, as we know. So that's quite interesting now because it turns the expression of the covariance into an expectation over the frequencies now. Okay, so instead of looking at the space of the variables, of the input variables, now we can look at the space of the frequencies. Okay, and what we can do now, we can actually sample from P of W given theta, and then try to average out these complex exponentials. That, of course, if this guy is real, we can just forget about the complex part here and just keep the rest. If you do a bit of not so intricate trigonometric expansions, then you can actually then approximate this guy, as we said, with a Monte Carlo approximation with number of random features here being the number of Monte Carlo samples you draw from this. And this Z here now is a cosine and sines, okay? So don't look too much at the details here, because what you really end up with is something which tells you how to construct this phi, this low-rank representation for K. And the way it works is that you take, at each layer, you take the layer before, you multiply by a bunch of weights omega. As I said, I just put it capitalized from before. And these omegas are sampled from the frequencies that determine how the covariance is constructed. We do cosine and sine, so we apply element-wise, and then we apply some, just scaling here in front. And now our functions are just going to be phi times W, okay? So this is what the connection with the Bayesian deep nets tells us, okay? With shallow Bayesian, infinitely wide neural nets. So effectively what we're doing here, we're just stacking Bayesian linear models, okay? So interestingly here, so if you use the RBF, you get the cosine and sines. If you use arccosine, you get rectified linear units activations. But this is really the picture I wanted to show you. So now this is not a graphical model anymore. Now this is an actual deep neural net. So what we end up with is that your inputs are going to be multiplied by a bunch of weights, omega, that have a prior distribution which depends on the covariance that you choose, okay, and the covariance parameters. Then you do this expansion, you get the phi, which is going to be where you apply nonlinear transformations. It could be sine and cosine, ReLU, depending on the covariance you have, okay? And then you pull everything together again with your W. Now this is a bivariate Gaussian process, for example, and then you keep going. You re-expand with a set of weights, and then apply nonlinear transformation, and you keep going, okay? So now, by doing this, you end up with something which is a Bayesian deep net, really, okay? So here now Y is, you can have a likelihood, Y given F2, and so now we can learn these models using all the tricks that people have come up with, all the fancy, super fast, scalable, tricks to learn these models at scale. Okay, so this was a simple idea we had that came to me when actually Andreas Damianu came to give a talk when I was in Glasgow before, University of Glasgow. And I thought this should be very simple, right? So you have if you can approximate a Gaussian process in one single Gaussian process in this way, you just stack them up, and then you end up with something which is a Bayesian deep net, and then you learn it using standard techniques. And that should be quite easy to do, right? So compared to now, if you look at the comparison with other methods, so here these are the two methods we propose, so DGP, RBF, and arcosine with the random features, okay? And we compare with the DGP expectation propagation that at the time was the state of the art, and just plain deep nets with the dropout, and then variational Gaussian processes, the Titius 2009 sparse GP shallow, okay? So what we show here is error rate and mean negative test log likelihood. So as we train the model, we report error rate on test data and test log likelihood. So the lower the better, okay? Because this is a negative test log likelihood. Okay, so what we see is that we converge very fast compared to all these EP approximations, and because they're very intricate, okay? Our is very straightforward. It's just a Bayesian deep net in the end, okay? Okay, this is an interesting one. This is MNIST, and now bear in mind this is MNIST without convolutional layers. Okay, and with MNIST, of course, without convolutional layers, you can only achieve like 2% error rate, which is not that great. Okay, MNIST, most of you have, I'm sure, they have achieved at least 99-point-something%. Yeah, with Gaussian processes, people have never really gone beyond 96 before this study, 96%, okay? And now, this is interesting, because if you look at our method, they converge quite fast, and also just plain deep neural networks with the dropout. Our competitor at the time could only do one iteration in the same time we trained our model, okay? And now I know that they improved the code, so this could be something that they may have improved, okay? But interestingly here, you see that the error rate of the deep neural network is a bit better than our DGP, but actually the test log likelihood goes up. And the test log likelihood goes up because it starts overfitting. So here we should have done probably some extensive tuning of the dropout rate, okay? But of course we haven't done it, and this is, with a sensible dropout rate that achieves, in any case, good error rate, your probabilities are not going to be so good, so your test log likelihood, so your model is going to be confident things where it shouldn't be confident, okay? So being Bayesian is good. That's the bottom line, yeah? So you're in the right place. Right, so just a bit of advertisement for some other work we've been doing for UAI 17. So we did, so in this work, actually, on deep Gaussian processes, we actually have a variant of, we tried the MNIST 8 million. I don't know if you've ever seen it. It's a variant of MNIST where you have, the data set has been augmented. And finally, even with something which does not have convolutional layers, we achieve 99% accuracy. We could also do it with inducing points in separate work, and this is the work at UAI, but I'm not going to talk about that, okay? So we can actually train on millions of observations, okay? This was run on a laptop, I remember. The beautiful thing now about being Bayesian is that we can do model selection, right? So finally, I'm showing here the same plot as before, but now it's only our model with 2 layers, 10 layers, 20 layers, and 30 layers. And we compare with another method that was comparing, was applied to this airline data set with 5 million observations, okay? And now it can do model selection. We can try to use the negative lower bound to do some sort of model selection. So in this case, it seems like 10 is a good way, well, a good number of layers. And also this is kind of backed up with the fact that the error rate is good, and also the test log likelihood. I've been warned about using the NALBO as a proxy for doing model selection with Bayes factors because it's just a lower bound. We have to remember that this is not exact marginal likelihood, okay? So In our case, it worked, but there might be cases where doing model selection with the negative lower bound is not a good idea. Okay. Okay. So now I think I spoke already for 1 hour. Okay, good. So what I would like to talk to you about now is this quite interesting recent. There's been a bit of interest on combining convolutional nets with deep Gaussian processes. Actually, with shallow Gaussian processes. We were the first to do it with deep Gaussian processes, just because we could. Okay. And I want to talk to you about this because I think it gives a lot of reflection for a lot of ideas for reflection. Yes, we have one question. Yes. I don't think I heard you, so I'll move closer, sorry. $26? Yes. Sorry, I'll move closer. Thank you. Yeah.
Why the averaging along the frequencies give us a gain when we approximate the narrow network parameters? I mean, on the previous slides, we have a Q distribution, and this is a
So here we're still at the modeling level. So before we were talking about both modeling levels. So here we have a way to do an approximation at the modeling level where we introduce extra variables, yeah, and then we use different techniques to learn Q. In our case here, what I'm saying here, this is a way to do the model approximation. So here you find an explicit representation, if you like, and finite representation for what looks like something which will have covariance, which looks like K. Okay, so here I'm just saying that if you use these Z vectors, which are a bunch of cosine and sine with frequencies drawn from this, then if you stack them together, you're going to get something, a phi, that if you do phi transpose, you get something which is kind of close to K. Okay, and then after that, now by doing this, I introduced omega and W to do this. Okay, because this is a Bayesian linear model now with phi as your features. Now you create this new extra random features, as we call them. Random because you draw this M, you draw them from P of omega, okay? And now, once you have this covariance, now the connection with Bayesian, well, shallow, infinitely wide Bayesian deep nets tells us that, you can just do a Bayesian linear model with this phi now as your new features, okay? So now, to do the Bayesian linear model, I need W. So now I have omega and W, which are the parameters I created, if you like, to do the approximation of my deep Gaussian process. Okay? And now, this is now what it is. It's just a Bayesian deep net with finite, you see, number of phi here. And now I can use whatever I want. I can use Markov chain Monte Carlo. I can use stochastic variational inference. You name it. Does that answer your question? No.
Okay, thank
no,
you.
I mean,
I think it's a bit clear, but I should think more.
Okay. Okay. So there's been a lot of work now on understanding the properties of convolutional nets, and so we know that they give problems in being too overconfident, and being Bayesian is good, and all these sort of things, and. The way they work, we all know. Okay, this is just a copy of the famous diagram in Yann LeCun's paper, and there's been work showing that actually, if you train these models with modern architecture of convolutional networks that are very deep, and so you introduce a lot of parameters, then you run into some problems. And the set of problems we're going to talk about now are the following. So there is a concept of that people care about when they do quantification of uncertainty, which is called calibration. So imagine now your classifier outputs. It's a binary classifier, just to make it simple. Your classifier outputs probabilities or scores between 0 and 1, even. Okay, not necessarily probability. Then what you would like is that if your classifier predicts 0.8, you would like that actually this is a correct assessment of the probability of class label, okay? Positive class label. And how can you do it? How can you measure it empirically? Well, if you predict on a lot of test points, you can take all your 0.8 predictions, and you can actually measure how many times, you can count how many times you actually get a label 1 or 0. And you would like to get 80%. Yeah? Does that make sense to everyone? That's pretty sensible thing to ask, right? And not only I want 0.8, I want this to hold across the whole values of my outputs, okay? But what happens in practice is that, your classifier can be underconfident. So when you predict 0.8, actually that was almost 0.9. And of course, if it's binary, it cannot be, it has to have this S shape, okay? So because it's the probability of one is one minus the other, okay? So you're gonna end up with the diagrams that look like this. And what you can do now is to say, well, you can extract some measures from this. You can say, well, how distant am I from the straight line here? And this is called the expected calibration error. What is the maximum calibration error I do? So what is the maximum of the distance between the points and the straight line? And these are ways to extract some sort of calibration measures that you would like to be 0, okay? And then there is another one, which is the Breyer score, which is something different, which can be actually decomposed in 2 parts. The Breyer score measures the distance between the labels themselves and the probability, L2, okay? So it's a L2 norm between these 2 quantities, labels and outputs, okay? And and that can be decomposed as the actual loss and a calibration error, okay? So in practice, you want these errors to be as low as possible, okay? And what happens is that actually, for modern convolutional neural networks, what happens is that you get these sort of diagrams where you are overconfident. So when you predict 0.9 is actually lower, okay, for example. Okay. And well, no problem. People have come up with ways to do post-calibration. So you have your training points, you have your test points. You keep some training points aside. You call them validation. Okay. You learn your classifier and your training points. Then you predict on the test, and then you say, you predict on the validation, and you say, okay, now I can correct my outputs a little bit to make this squiggly line look like a straight line. Okay. So you can kind of compensate. You learn a transformation of the output so that your classifier becomes calibrated. So when I talk to people that have done this for many, many years, they look at me like, so what's the problem? I mean, you can actually do it. And I'm not against that. And I believe that this is actually a good way to do calibration. But it turns out that what happens is that you have to set aside some training points to do this. And when you set aside training points, well, you use less points to train your model. And if you don't have that many data points, then maybe this is not a good idea. Or maybe if your model is very complicated, you need all the data you can have to actually train it in a better way. And our experience is that if you leave out some data, you always achieve lower performance, which is kind of, everyone's experience, okay? So wouldn't it be great if we could do a classifier that is calibrated by construction, okay? It turns out that the calibration is, if you use the right loss for the right observation, so if you use the right likelihood, so if you're in a regression and the noise is actually Gaussian and you use a Gaussian likelihood, you have guarantees to be calibrated. If you have a multi-class problem, if you use the softmax transformation of the output, which corresponds to the multinomial, then everything is calibrated. But the problem is that if your model overfits or is overparameterized and you don't regularize properly, you're going to lose this property of calibration. And this was studied, as I said before, in this, I have it somewhere, yes, in this ICML 17 paper, okay? Okay. So then people have come up with ideas, said, well, I mean, we know how to do Gaussian processes. let's do Gaussian processes, which are good for quantification of uncertainty, and then let's replace the fully connected layer here with a Gaussian process. Great idea. And we have at least 3 works that do this, okay? So this was Wilson 16, Bradshaw 17, a group at Cambridge, and this is our group this year, 2018. We've gone a step forward, of course, because now we can do deep Gaussian processes with millions of observations, so we can even stack deep Gaussian processes. And I have to tell you the truth, I mean, we've done it just because we could, right? So we said, well, we could do it now, so let's do it, okay? But then we started asking ourselves some questions, because do we really get any good quantification of uncertainty by doing this? Not at all. And actually, in this study, in this study in our archive, we actually study what happens if you do this sort of combination of convolutional nets and deep Gaussian processes, shallow Gaussian processes, and we compare with state of the art, and it turns out that this is not a really good idea. You don't get any calibrated classifier. And performance improvements? Not really, okay? So this is kind of maybe a negative point about the kind of things that people have been looking at in my community, so this is also criticism for myself, okay? And it's something I wanted to share with you all. So if we look at the competitors, so these are the 3 works that I mentioned before that are the state of the art in convolutional Gaussian processes. So this Bradshaw and others, we refer to GPDNN, so it's a hybrid combination of convolutional nets and Gaussian processes learned with inducing points. So this is very much like Titia's 2009 approximation, extended stacking convolutional layers before. The stochastic variational deep kernel learning proposed by Wilson in 2016 uses another kind of approximation that is quite clever. It uses inducing points again, but it uses a lot of inducing points. And they can do it because they use a structured position of these inducing points so that the algebra becomes quite straightforward. Okay, so we're talking about Kronecker matrices, Toeplitz matrices. I'm not going to go into the details, but this is an idea that was proposed by Wilson himself before for shallow GPs, and then it's been extended to convolutional layers stuck at the bottom of a Gaussian process. Okay, then there is this other work on convolutional Gaussian processes, which the legend is missing here, I think. Yes. There's something wrong with the legend, unfortunately. Then we have convolutional Gaussian processes, which, for which we have, instead, it's a Gaussian process, and the way the covariance between points, between images is computed, mimics the computations that you do in convolutional nets, okay? And then with this, we have, well, these are the 3 methods. And I wanted to tell you the name of the data sets, which was in the legend, which disappeared, of course. So here we have 3 data sets, for sure. And 3 architectures. So now I'm sure it's CIFAR 10, CIFAR 100, one with a shallow, one with a deeper convolutional network architecture. I don't know. I don't have the labels here, so I'm lost. I'm sorry. For some reason, this figure should be different, but I don't know why this is the case. But in any case, so we can see is that all these classifiers are overconfident. So they have this pattern that we saw before, where you know, this is the kind of probability you predict, and this is the actual probability. So you see, you always kind of tend to be overconfident. And this, as I said before, are combinations of convolutional nets and GPs. So that means that, for some reason, we're not improving on quantification of uncertainty at all. Okay? And then we stumbled upon this other piece of work with, this is what Yaringal proposed in their 2017 paper on convolutional Bayesian Monte Carlo dropout applied to convolutional nets. And it's quite striking the fact that there were not many Bayesian convolutional nets before. So I was looking at references when I was writing this paper with my students in, this year, and we're looking back, to find the first Bayesian convolutional nets. You'll be surprised that pretty much, well, we haven't found anything before Yarin Gal's work in 2016, 17, on people doing, being Bayesian about the convolutional filters. So nobody applies stochastic variational inference, Monte Carlo dropout, or whatnot, to, or Markov chain Monte Carlo, for that matters, to convolutional layers. And why is that? Well, I don't know, but we were kind of surprised. And one reason could be that it's already very expensive to learn convolutional filters in convolutional nets, that also applying some sort of variational inference on that would be crazy. But this connection between Monte Carlo dropout, between dropout and Bayesian inference, variational inference, actually allowed also the authors of the original study to actually have a simple way to be Bayesian about the filters. And here, this is the first time that we actually studied their work, and we actually see that they are very calibrated. Okay, so here what I'm showing is a CIFAR10 with a Linette architecture, and this is just a convolutional net. There is no Gaussian processes here. Okay, and this is a CIFAR10 with ResNet and CIFAR100 with the ResNet. And what I'm showing here, we are subsample 1/8 of the data set, 1/4, 1/2, and this is the entire data set. Okay, and you see that the reliability diagrams tell us that these classifiers are actually pretty well calibrated. Okay, the histogram here shows you also the kind of the distribution of the how many times we predict a certain value. Okay, and especially for when we subsample heavily the data sets, you see that still the calibration properties hold. Okay, so this was kind of I think very interesting result that shows you already that if you take just a plain convolutional net and you do something which is Bayesian, so you somehow regularize the filters, then you achieve calibration. Okay. So one of the issues that, as I said before, these modern convolutional nets have is that the filters, when they are so deep, the models are so complex that they tend to do some overfitting, which you can sort of compensate with the regularization. Okay. And now what we did was to do the same thing. Now we stuck our deep Gaussian process now on top of this these convolutional nets, and we did the same thing. We did Monte Carlo dropout for the filters and the variables inside our Gaussian process approximation. And you see that, again, we recover something which is quite nice and quite calibrated. Okay. So now if we compare with all the competitors, we are the red ones. Okay. So here it's two different ways of doing random feature expansions. I will not go into the details. Green are plain convolutional networks with ones with the Monte Carlo dropout and the other one with post-calibration. You see already that the post-calibration is the dark red. It always achieves sort of higher errors, you see. And that's because you use less data, because you need part of it to do with the calibration. Okay. Maybe you cannot really appreciate the difference, but so here what I'm showing is that, okay, error rate for two different data sets with a shallow convolutional structure, test log likelihood, and then these two calibration measures, okay? And you see that these guys are not very well calibrated. Instead, what we do is something, because we regularize the filters, somehow we achieve same performance as just standard convolutional networks with Monte Carlo dropout. But then the question is, well, you don't do any better. So why do you do it? Which is a good question. And same thing, if we go deeper for a deep convolutional structure, you see that, again, post-calibration achieves a good calibration, but on the other hand, gives you a lower accuracy. And instead, if we do now this thing that we do, we achieve something which is very good and state-of-the-art. But you see, also, I mean, now with this, we achieve performance that the literature on Gaussian process never could dream of course, because now we use convolutional filters, okay? And yeah, so then now we can go crazy and go deeper with the GP that we put on top of the convolutional layers. We can go deeper, and actually if we go slightly deeper, we get a slight improvement in error rate and slight, but you see here the values are so close to each other that, you know, slight worse calibration, okay? Even though this other score tells us that also the calibration there is good. Okay, this is just a minor point to say that we can now also stack deep GPs on top of convolutional layers. There was so much more I wanted to tell you about, but I think I bored you enough with this. If you're interested in DGPs, there's been work on autoencoders, so they can also be used for unsupervised learning. Variational autoencoders, the same way you probably know, extended with deep Gaussian processes. This was Neil Lawrence's group in ICLR 15. And we did something with my PhD student also this year on just plain autoencoders, just replacing decoder and encoder with a deep Gaussian process. We did something with deep Gaussian process with constraint dynamics this year, ICML. So in case you have some physics that tells you that functions should obey some differential equations or some monotonicity constraints, it's actually something you can actually embed in the framework of deep Gaussian processes, stochastic variational inference, and so on. Okay, I think I have 10 minutes. That's great. So the big question that a lot of people ask me is, why do you still do GPs? Well, at the end of the day now, we've come to the point where there is a very thin line between deep Gaussian processes and deep neural networks, I think. So I see myself as a person that works now on both fields. And you can think of deep Gaussian processes as a way to maybe impose sensible priors. So when you have to think of priors for Bayesian deep nets, I usually say, okay, I use some sort of rule of thumb, maybe the Xavier rule to do some sort of scaling of the variances of the weights at each layer, or maybe I do some just 0, 1. Why not? But then this has implications on the kind of functions you get, on the kind of functions you can get from this prior, from this model. Okay. So if you think in terms of Gaussian processes instead, because the functions will be determined by the covariance function that you choose, and the covariance function induces, in our approximation, certain priors for the weights, then this is a much neater, I think, intuition on the kind of priors you can devise for Bayesian deep networks. So I think this is maybe one of the advantages that still we have if we think about deep Gaussian processes as opposed to Bayesian deep nets. But at the end of the day, they're very similar. I hope I convinced you that the inference for DGPs is extremely hard, okay? So what we do, what every work does is to do a model approximation and then approximate Bayesian inference on that model. So we have two levels of approximation. And I think we haven't gone nearly enough to understanding the implications of doing a model approximation and approximate inference on these models. So what we end up with is something that is not really a DGP anymore, okay? Because we truncate the infiniteness of the layers, and then we apply fully factorized posteriors over the weights of our Bayesian deep net, which is, well, a pretty heavy approximation. And I think we haven't studied this very much, okay? But I think this is an issue also for the Bayesian deep nets community. So we're trying to, well, we borrowed a lot of ideas from Gaussian processes, kernel methods, deep learning. So now we can do stochastic-based approximate inference. We use this idea of low-rank approximate decomposition. And in various works, we're now exploiting algebraic computational tricks to actually compute these matrices much faster. Okay, so this approximation here, you have to draw M to construct M features. You have to sample M frequencies in our approach. And the way you do it, you first take your input, multiply by M by M matrix. But now, of course, this is going to cost you M cube operations, M squared operations, sorry. M by M, N M squared operations, yeah? So it costs you M square operations. And if your input is M dimensional and you want to create M features, this is going to cost you M square, right? So now, well, the idea would be to say, is it possible to lower this computation? So we are multiplying by a Gaussian random matrix. Gaussian random matrices have some long history, and people have come up with ways of constructing M by M Gaussian random matrices just by starting from m Gaussian random variables. And you can do these computations vectors times, well, Gaussian random matrix times vector in order m log m operations instead of order m square, okay? So with these algebraic tricks, then we can construct many more features. We can really expand the applicability of these deep Gaussian processes and get closer to what is the infinity of the number of features you would need to approximate the Gaussian process exactly. So at least in this sense, we're trying to at least solve the issue of model approximation. I maybe conclude with this slightly disappointing note on the combination of GPs and CNNs to be slightly disappointing. We were hoping to get a slightly better performance and maybe improve on state of the art of CNNs. And well, maybe it was expected, right? So all the weight, the heavy lifting is done by the convolutional filters in convolutional networks. You just put a bunch of fully connected layers and you're good to go. So maybe that was something we should have figured out before. But unless you try, you never know. And regularization of filters is necessary. So if you want to do a good Bayesian convolutional net, be Bayesian also about the filters. That's my take-home message. And yes, so before concluding, I just wanted to say something about a little announcement. So we're hiring various levels from PhD to assistant professor. If you haven't noticed, we're here, okay? So I was in Scotland before for many years, so God said, okay, now you can move to this place and enjoy the beach. So we're working a lot on this topic. So if you're interested, of course, feel free to get in touch. None of these positions has been advertised yet, so the advertisements will come very soon, just in case you're interested. I'm funded by a 7 years chair. I have to thank AXA Research Fund whenever I give a presentation because they support my research. And I put a long list of references at the end of the slide so that if you're interested in reading more, you can find a lot of references. Thank you very much.
Thanks for a great talk.
Thanks.
You seem to have done a fantastic job in marginal or in working with uncertainty within the model in these deep Gaussian processes. At the same time, I've seen that you address different configurations of nets for the same data sets, right? Simultaneously, you have obtained the estimates of the lower bounds of the marginal likelihoods for all of the models. So the question is whether you have ever tried to incorporate the model uncertainty by means of putting the prior on the model configuration, right? And then performing Bayesian model averaging of whatever you need to do with respect to different configurations.
Great question. No, we haven't tried. I think this would be an interesting exercise to do. Definitely. No, we haven't tried, but I think, yeah, there is a lot of value into what you're saying. So it's something we should probably look into. Yeah. Sorry, we haven't tried, but thanks for the great question. Yeah.
Hey, so this is a great talk, very interesting,
Thanks.
especially on the combination of GPs with CNNs. So you show that you can get nicely calibrated measures of uncertainty from by playing Monte Carlo dropout to GPs and CNNs in the filters. It's nice. But how does having well-calibrated measures of uncertainty, according to your expected calibration error rate, for example, allow you to say whether you have made an error or not in this particular one classification? So like you have an X, you're classifying X. Can you tell, like, have I classified X correctly or not based on calibration? Does calibration help with that? Or is calibration more a sort of averaged over your data set kind of measure?
Well, great question. Yeah, this is, maybe I can repeat the question. So whether these calibration measures, can tell you anything about when you're given a new test point, can you say something about, well, is this calibrated or not? Well, unfortunately, these calibration measures that I showed here are sort of aggregated across some sort of test points, yeah? So they don't really tell you much about, if you have an online, let's say, decision-making process, they don't tell you, well, is this going to be calibrated or not? Because they tell you some sort of average behavior of the classifier across a lot of samples. Then there are also criticisms on expected calibration error, which is an L1 sort of measure, because it measures the absolute distance between your reliability diagram. Here, it's going to be an L1 absolute value, okay? So it can have some issues, and also the distribution of the predicted values sometimes can lead to issues. So I don't think that ECE, for example, expected calibration error, has been it's the only way to look at the problem. So that's why it's good to use multiple measures to do it. But to specifically do what you're saying, I don't think at least I wouldn't know on top of my head how to do it. Thanks. Any more questions? No? Yes?
When it comes to these CNN and GP models that we combine together, what kind of priors do we put on the parameters of these filter maps?
What kind of so repeat the question. What kind of priors should we put on the filters when we combine them with GPs or even when we do Bayesian convolutional nets, perhaps? Good question. I don't remember what we did. So you catch me off guard here. I don't remember what we did, but so the connection is, well, doing Monte Carlo dropout is equivalent to doing some sort of variational inference. And then you're going to have some, you can if I remember well, we have a parameterized prior with a hyper prior, alpha, and that parameter we learn. So it's possible to learn the optimal distribution of the prior looking at the problem. So you interpret this as a model parameter, yeah? So it's I know that learning the prior sounds weird, but it's not effectively what we do. I mean, this is something that people do a lot, When you have a prior on some parameters, you can parameterize that prior with an extra parameter for the variance, for example, and then you try to learn. If I remember correctly, this is what we've done, but I would like to double check that. Unless we put 0, 1, I don't know. Yes?
I guess a follow-up to that, if you have like a geometry kernel, right? Do you factorize your prior spatially correlated pixels?
If we have a 3 by 3. Uh-huh.
It's just like the top left pixel, so to say, has a different weight, correlated with the one below, right?
I think at the moment, I mean, if you think of it as when you do Monte Carlo dropout, effectively this connection with variational inference tells you that you're doing fully factorized. So at the moment, that doesn't account for any correlations among the weights. And we said that we tried variational inference with fully factorized Gaussians, and we got lower performance. And now what I wanted to try is something, as you say, we have code to do non-factorized, so, we can impose various correlations across, and we could try, but because of the Monte Carlo dropout really works with, it's like approximating your posterior with a mixture, yeah, for each variable in turn, because you have some mass on 0 and some mass on 1. It's a bit degenerate, of course, because it's delta spikes, yeah. But then when you multiply them together with all the approximate posteriors across all the parameters, you get a huge mixture, yeah. And that somehow gives you good performance that you cannot. I mean, we cannot mimic the same with just fully factorized Gaussian approximate posterior. So more work to do on that, I think. Maybe using some of these hyper networks to do, complicated posterior shapes and so on. Yeah. Yes.
how many time, for example, did it take you to train it for Cypher?
How many times do you take?
How much time does it take to train it?
To train. Okay, now we bought some fancy GPUs where we work, and we run all these experiments. For example, we run for 6 hours, I think. All these examples that you see here, I think they run for 6 hours. Yeah. And we use GPU P100, yeah, which is quite powerful, yeah. We spent a lot of money on that, yeah. But yeah, I mean, at the end of the day, for example, our approach is very similar to what you would do with it's almost like a convolutional net with fully connected layers. When you have, a GP, we approximate with 2 layers in the end, right? So pretty much it's the same thing. Yeah. So you're not going to lose so much in terms of time. Yeah. It might converge slower, yes. Time for coffee, I guess. We're a bit late, eh? 5 minutes late, sorry.
Thank you, Maurizio.
Thanks. Thanks a lot, guys.